Welcome back to the second lecture of the day, and we will continue with the loss function. Thank you. Okay, so welcome back. I hope everyone's nice and awake after a coffee. What I said at the start of the first section is that essentially when we're training a neural network, which is just approximating some function, well, we really have three ingredients. First, we need to decide how to parameterize the function that we want to use to approximate the function we're interested in. This is all about the architecture. Then we have to define some kind of loss function, which is what we're going to be minimizing, and everything works on some kind of optimization principle. And afterwards, then we actually have to do the optimization itself. Okay, so we have the three sort of theoretical sessions and the three ingredients, as far as I'm concerned, are the most important parts. So we'll be talking now about the kind of loss functions that turn up. Now, again, this comes with a really, really big caveat. I'm mostly, well, almost exclusively going to be talking about loss functions for solving like elliptic PDEs. Okay, so some of the things might work in other problems, some of the things might not work in other problems. In other problems, there may be things which are qualitatively very distinct. So coming back to the kind of point I wanted to make at the start, I mean, this is just to try and give you guys an idea of the kinds of things that you can do and the kind of language that people use when they're talking about these kinds of problems. Okay. So I think the first thing to emphasize is that, I mean, at least almost every loss function that we can find when we're talking about solving PDEs with neural networks, and this is going to be defined via integrals in one way or another.
Sorry.
Now, there is a big problem with neural networks is that there's no sort of exact quadrature rule. So if you're used to things like finite elements, then the whole issue of integration, okay, it might be expensive, but it's doable, right? I mean, if you have some piecewise constant function basis on a given mesh, you can use Gauss type rules, and you know that all of your integrals are going to be exact, at least up to, you know, sort of rounding errors and things like that.
Yeah, may I ask you to share the slides?
Oh, is it not showing up on the Zoom?
Okay.
You're right. Okay, can they see now?
Yeah.
There we go. Okay. Okay, so if you're working in like, yeah, finite element type bases, spaces, and you have some fixed mesh, okay, it might be very expensive, but at the very least, in principle, you know how to integrate exactly. Now, this isn't true when you're talking about neural networks, right? If we're thinking of some problem where our solution to the PDE or ODE or whatever is a neural network itself, I mean, essentially, there's too many degrees of freedom to be able to identify a rule. I mean, a lot of typical quadrature rules that are exact over certain spaces, I mean, these are exact over finite dimensional spaces. And neural networks don't form finite dimensional spaces. If we just think of tanh x minus b, where b is a parameter, by changing b, we have a continuum of linearly independent basis functions. Okay, so we can't even think about the possibility of having over these kinds of spaces an exact quadrature rule. So we have to do some kind of numerical integration, and we have to accept that there's going to be errors and do what we can to try and not have them destroy our solutions. Now, first, I'll talk about what happens when we use a fixed integration rule. I mean, this is not a good idea to use, but I want to show you what happens, or what can happen at least, when you use them. If we try to do some kind of comparison to interpolation type problems, if we think we have some data and we want to use a network to approximate it, we can think of this as being like having a finite data set. But the difference is we're using a fixed integration rule on a finite number of points, which is somehow our data. Now, in the language of more data science-y approaches, what they'll say is that the ability for your solution to be correct outside of your data, and this is the generalization of your solution, and the generalization error, well, this is how bad you are away from your data points. So when people are talking about data science applications, they talk about things like batches, they talk about splitting into training and validation, but we're kind of going to ignore this issue for reasons that will be apparent later. Oh, now this isn't working. Off the batteries died. Ah, there we go. Okay. So just thinking of a simple interpolation problem. Okay, this isn't our interest, but we just want to see what overfitting looks like if we do an interpolation problem where I have input-output pairs, no derivatives, no PDEs. So I've made some very small data set, which is basically a sine type function with a tiny little bit of noise that I stuck into it. Okay. So in the spirit of data science type applications, I've taken some data, I've taken some to be my validation loss, I've taken some to be my training loss, which I use to estimate this kind of mean squared error. And I look at how these guys evolve when I'm training. So especially because of the noise, I mean, what we can see if you look kind of carefully, so at the end of training, my training data is very low, my validation loss has gone up. So on unseen data, I'm now doing worse than I was here. And you can look at the picture and you can see that this final neural network going through these data points, which are in sort of red circles, it does very well at the data points, but away from them, it's doing crazy things. Okay. So at the very least, our solution is somehow correct at the data points, even if it does strange things away from them. Now, the typical strategy when you do this kind of problem would be to say, okay, we monitor the validation loss. When it starts going up, we know there's a problem, so let's stop training. Okay? Now, if we have a loss function when we're involving the derivative, then something slightly different can happen. Okay, so here we're just looking at a very simple ODE, not even a PDE, not even second order. So the derivative of my function. So here we have the Heaviside function. So for x less than 0.5, my function is 0. Afterwards, it's equal to 1. Right? So my solution should be this kind of ReLU-looking guy, which is 0 and then linear afterwards. So it's not especially clear maybe for the people at the back, but I'm going to do exactly the same idea. This time, I don't introduce any noise. I just evaluate essentially the difference between the derivative and my Heaviside. I take this value at all of these data points, I square, I sum, and I try to minimize. Okay? Now, what happens in this situation, which is a bit different from the case where we had the interpolation problem, is that what we can see is that at the data points, I'm not agreeing with my function, right? I mean, it's parallel to my solution, but it's not equal to the solution, right? And this is because it's the derivative which is correct at the data points and not the function itself. Now, this is really easy to explain in a one-dimensional example where we just have derivative is equal to something. And if my derivative is correct at data points and maybe doing strange things at some other points, well, it's going to be parallel. Now, if I have a complicated PDE here, and I'm satisfying the PDE at certain points, but not satisfying the PDE between the points, I have no idea what the solution could be like, right? I mean, this is going to be a much stranger structure, even though in this case, it's really simple. And essentially, what's going on is that here, I mean, everything's going more or less correct. Because of this discontinuity here, something strange happens. And then afterwards, the derivative is correct, but because somehow when we integrate this solution, we're off by some number, this number propagates. Okay? So essentially, really the thing that I want to get at from this picture is that overfitting when you have a PDE type problem can give very different behavior to when you're doing an interpolation type problem. Right? I mean, somehow it's the PDE itself that you're overfitting on, rather than going through your data points in the correct way. and the error will somehow be in the null space of your PDE, which could be huge. Right? So what is the easiest way to avoid this, and the way that basically everyone does it, is they don't use fixed integration rules. Okay. The standard approach is to take a stochastic rule. So what that means is that at every iteration in my training loop, I generate new data. I generate new integration points. So the standard choice is Monte Carlo. Okay, we just take some random uniform sample of a given number of points inside our domain of interest. And at each iteration, we approximate every integral just by taking some appropriately weighted average of evaluations of our function at these points. And we claim that this is an approximation to our integral. At least this is an approximation in the sense that the expected value is the exact integral, as long as our integrand is nice enough. And the variance behaves like 1 over the number of points that we've used to do the integral. Okay, there's obviously some constant here. In reality, right? It's O1 over n, not literally 1 over n. This is just something which I like to emphasize. I mean, people always say that the error is of the order of 1 over square root n. Right? I mean, this is the error in the sense of like a mean squared error sense. If you give me a particular sample, it's possible, even if it's unlikely, that the error is much, much, much bigger. Right? I mean, this is the mean squared error. This is not a uniform estimate, like the kind of uniform estimates you might expect with Gauss rules. One point I want to make before moving on, actually, if we're in a relatively simple geometry, Monte Carlo sampling is really cheap, right? If I'm on something like the interval 0, 1, sampling 1,000 points independently on 0, 1 costs basically nothing in comparison to evaluating the integrand at all of these points, okay? So it might be tempting to think, well, if I'm sampling new points at every iteration, isn't this really expensive? I mean, it's far less expensive than all the other things that are happening in each iteration. Okay, so it's kind of like a negligible cost, at least if you're in a simple geometry. If you're in a very strange geometry and Monte Carlo sampling becomes very difficult, it might be a different story. I mean, if you're on a square or a circle or something like that, it's not going to cost basically anything. I said this is definitely the most used method in neural networks. And one of the reasons is that, as I said earlier before, I mean, neural networks, they're mostly used because of their scalability properties. Right? I mean, neural networks tend to be much more efficient at approximating things in very, very high dimensions with regards to the number of trainable variables that you have. But if you have a very, very high dimensional integral, okay, this is also complicated to do. But with Monte Carlo methods, we see there's basically no reference or no direct reference to the dimensionality of our integrand nor our domain in this problem, right? There's this constant, which I guess implicitly, so this is the difference between the integral, the mean integral and f itself. This implicitly depends on the dimension that we're in, because obviously a function defined over the 3 cube and the 2 cube are not the same function. Right? So there's a dependence here, but I mean, it's not like Gauss rules where you have factors of 1 over d in the exponent, which mean that integration becomes very, very slow once you get into higher dimensions. Okay, Monte Carlo is in a sense resistant to the curse of dimensionality with respect to integration, just like how the neural network is resistant to the curse of dimensionality with respect to the expressivity for a given number of variables. So very oscillatory integrands may have much higher variances, but either way, our scaling is still going to be some constant depending on the integrand over n. But this variance can still be surprisingly big. And this is like a one-line computation. If you want to just integrate this very, very simple sine 2 pi x function and have your mean squared error of the order of 10 to the minus 3, then you need like 500,000 points. And this is a lot, right? And one of the ideas of, can we do something better? Okay, somehow you might hope that if the expected value is correct and you do thousands and thousands of iterations, I mean, these errors are going to even out, so it's not that big of a problem. But we can still try and do something better if we're in other situations. The simplest method, if we're in low dimensions, in my opinion at least, is stratified Monte Carlo. Okay, we just think rather than taking, say, 100 points uniformly and independently on our domain, we chop our domain into 100 equally sized bits, and we take 1 point at random from each. Right? In the spirit of a Gauss rule, if we have a function which is piecewise constant on this integration mesh, then it's going to be exact. Okay, so in the same kind of style as the error estimates that you get when you use Gaussian integration on a mesh, you can obtain estimates in terms of the variance of this form. Okay, so now in this case, we do see, okay, so I haven't specified anything about the geometry, just a kind of uniform partition of the domain where we're using n points. Well, the variance now has this kind of scaling if we have a differentiable integrand, which is 1 over n to the power of 1 plus something. Okay? This is always going to be better than Monte Carlo, at least in an asymptotic limit, right? This is an asymptotic statement, not for a fixed m. So, but at the same time, we have this factor here, 1 plus 2 over d. D is the dimension of the space that we're in. Okay, this is kind of like a Gauss rule. This is the kind of scalings you get in the errors for Gauss rules of a given order. The higher the dimension, well, the worse this is going to be. Right? If we're in 1 dimension, now we have 1 over n to the 3, which is much nicer than 1 over n to the 1. But if we're in dimension 200, now we have 1 over n to the power of 1 plus 0, 1, which isn't much of a benefit. Once you add on top the cost of trying to make a mesh in 100 dimensions, which I'm not going to try to do. Right? But if we have some problem, I say my interest is particularly in the idea of parametric problems. I mean, the PDE lives in a small space, or low dimensional space, but it's the parameters that make the problem high dimensional. So the kind of integration over your computational domain, it may be much better to use these kinds of rules than using just a vanilla Monte Carlo. Okay? So here I just took a really, really simple integrand. I think it was, I mean, it's qualitatively sine 3x, right, on the interval 0, 1. And what I'm comparing is, after doing a bunch of samples, what's the difference in the variance between a Monte Carlo and a stratified Monte Carlo for a given number of points. Okay, so I have my number of points here. I go from sort of a handful up to about 10,000. These dotted lines correspond to the asymptotic scalings. And we can see we can really, really reduce the error significantly by using a stratified Monte Carlo scheme, right? I mean, here I'm at sort of 10 to the minus, 6, 7 or something like that. Whereas with a regular Monte Carlo, I mean, I've barely dropped at all, maybe by a factor of, well, you can calculate it basically explicitly. It should be by a factor of about 100, right? By using 10,000 points. Right? Now, this is what happens in 1 dimension, right? And when we have this huge difference in the asymptotic scalings and they enter into this asymptotic regime really quickly, again, emphasizing this is a really smooth integrand. If I had something more complicated, then the pre-asymptotic regime would be very different. Once we go into 3 dimensions, okay, we can start seeing this curse of dimensionality with respect to the scaling. Up until about 1,000 integration points, there's basically no difference between doing a Monte Carlo or stratified Monte Carlo scheme. I mean, they're more or less the same, right? We don't lose anything, but we haven't gained anything. But once we start getting beyond this and we get into these asymptotic kind of regimes, then we can start to see the benefits, where once we're at, there's probably about 50,000 integration points, we're talking about sort of order 10 to the minus 2 versus order 10 to the minus 4. Okay? So we get still a decent saving if we're using a lot of points, whereas in 1 dimension, and Monte Carlo does not make sense. Monte Carlo is designed for high dimensional problems, essentially. So Here is just some really, really simple implementation. I just take some very simple, smooth function. I think this was with about 100 integration points. And we just train the two where everything is the same. We start with the same initialization. We have exactly the same architecture. And the only difference is that when we're integrating our loss function to do our optimization loop, one uses Monte Carlo, one uses stratified Monte Carlo. But in this case, you can see our loss is doing quite a bit better. It's not quite as noisy. And then this is the loss, and then this is the H2 error. You see, beyond this sort of point, which would be a couple of thousand iterations, we can see that things are much better in the case of stratified Monte Carlo. And there are other problems where this effect can be really, really amplified when integration errors are much more dominant as far as we're concerned. So I mean, integration is like a whole thing basically with this. So you can go much further beyond just simply stratified integration rule, stratified Monte Carlo. I mean, there's more or less a whole world of Gauss stochastic rules, which are essentially exact for polynomials of a certain degree and stochastic at the same time. So they need more points than a Gauss rule, but at the same time, they kind of avoid this overfitting issue, which might happen if you used a fixed Gauss rule. Okay? As I say, if we use fixed quadrature, finite data, if we think of it in that way, then the kind of overfitting that we get can be very, very different. So, okay, there's all kinds of other methods, which are sort of the same methods that people would use in data science type application. There's regularizers. You can check things on a validation set and so on and so forth. But what we're doing, I mean, data is typically very, very, very cheap, right? I mean, if I'm doing some kind of problem where I want to get pictures and know if it's a cat or it's a dog, if I want to get more data, I need to get more pictures and tell someone to check if they're cats or dogs. If I want to do a Monte Carlo sample, I just try sample MC or whatever, and then I get new points before I've even pressed enter, essentially. So whilst Monte Carlo is the standard approach, I mean, there are other approaches in the world of stochastic integration that they're much better in lower dimensions, and these can be considered as well. And by lowering these integration errors, you can get a much better convergent scheme. Now, and integrating the loss function is one thing. I mean, okay, what we kind of supposed by talking about the integration strategies is that we've already decided in the continuum what our loss function should be, and then later we need to integrate it. But we should really go a kind of step backwards and think, what should our loss function be? Right? I mean, obviously, the main property that we want for a loss function is that its minimum should be a solution to the problem that we're interested in, right? Otherwise, it doesn't make sense to minimize it. But we want to go a bit further because in reality, I mean, these problems, once you put a neural network into a problem, you have a horrifically non-convex problem with lots and lots of local minima, lots of saddle points. Optimization takes ages. You know, if you're lucky, you'll get to some local minimum, and you kind of have to hope that it's a good local minimum. Right? I mean, you can't expect to reach the global minimizer. So we really want to say more than just the minimum is a solution to my PDE. We want to say if I'm near the minimum, then I'm near the solution to my PDE. Right? Now, near the minimum, okay, this is easy enough to understand. We have two real numbers, and okay, if they're near, right? When we're talking about functions, this becomes more complicated. Are we talking about in some L2 norm? Are we talking about being uniformly close? Are we talking about Sobolev norms? Okay, so the loss function that you use is essentially related to the kind of approximation that you want in your solution. I mean, somehow the holy grail, as I like to call it, is that if you're trying to get a good approximation in some norm of your exact solution, right? Okay, so I'm not going to specify the norm. I'm just going to say I want this thing to be close. Then the ideal loss function would have this kind of property. I mean, somehow the distance to my minimum should be more or less the distance to my exact solution in my norm of interest. If I change my norm of interest, I should probably be changing my loss. Yeah. So in order to talk about these kinds of things, we have to talk a little bit about function spaces, formulations, and so on and so forth. I mean, I'll try to keep this as light as possible for physics audience. But we're only going to be thinking about these sort of HK spaces, which I'm assuming you're more or less familiar with. Yeah, square into, yeah, okay, excellent. So, okay, we have our normal L2 spaces. We have the HK spaces where the first K weak derivatives are all in L2. And because we're going to try and make life easy for ourselves, we'll mostly be thinking about H1, 0. So we have functions which are 0 on the boundary in H1. And then we can use this norm, ignoring the order 0 terms, because we have a Poincare inequality. Okay? So if we do a standard pins minimization, then we're talking about strong form PDEs, right? In some sense, at least in an L2 sense, we need that the Laplacian of our neural network is in L2, right? And exists, I suppose. So we have some kind of differential operator. We typically also have some kind of boundary operator. So this could be the mapping from our function to its values on the boundary, or perhaps we have a Neumann condition or something like this. So just thinking of the simplest case where we have some boundary condition and some PDE on the interior, then we can think of conceptually a loss function of this form, right? Okay, we have some PDE operator minus our right-hand side. We take the L2 norm squared and put some weight before it. Exact same thing on the boundary. We put some weight before it, and then we have whatever is our mapping to the boundary values of interest minus whatever the value on the boundary should be. Again, we work with the L2 norm on the boundary. And this is how most implementations that you see end up working. Now, this is very, very attractive because, I mean, L2 norms is kind of easy to evaluate when we're talking about neural networks. We just have to do quadrature. Quadrature still isn't the easiest thing, but it's much easier than other norms that we might be interested in. Now, if we, for the next bit of discussion, we'll still just be thinking about this really, really simple case where we have our differential operator as the Laplacian, and we have some Dirichlet condition on the boundary. So, okay, the natural space for the strong formulation would be H2. Okay, so we're talking about cases where we have that the second derivative exists in some sense, at least. And then the natural way that we should be thinking about measuring the error would be something like this. Right? Now, if we have a sufficiently nice domain, then what we have is this almost holy grail type result that we hoped. If we exactly hit the boundary conditions, there's no error in the boundary, then we know that if we use this as our kind of loss function, then we have some control on the error in H2. If this constant a priori we may not know. But in practice, what people tend to use is this. Okay. Now, this is a little bit problematic because I'm not sure L2 on the boundary isn't really a very correct space to be working in when you're doing this kind of problem. And one thing to keep in mind, and if we're on something like the famous L-shaped domain, then this doesn't hold. Right? And you can have the classical example where you have your singular solution at the internal vertex. Its Laplacian is basically 0 at the vertex, but its H2 norm is infinite. Okay, so then you have to think a bit more differently about what norm do I want to be approximating my solution in. Now, we're going to forget about this problem that L2 on the boundary isn't really natural, and we're just going to think about this really simple problem here again, and just ask the simple question, I can easily put this into my computer, I can do an optimization loop. What should this W be? Okay. This kind of makes sense. If I have some penalty for the boundary term, maybe if I make it too small, I break the boundary condition, the errors propagate into the interior. If I make it too big, maybe this doesn't do enough. And what should the value of this parameter be? I'm just going to be thinking about the disk on R2, so we're finally moving into two-dimensional problems. And okay, the spoiler is that there's not really a clear-cut answer for this. So in this particular experiment I did, again, we see these kinds of noisy U-shapes. Again, If I were willing to leave my computer running for 5 days, then I could do 100 simulations with different initializations for each parameter. So this is really just a qualitative result rather than a quantitative result. But we see a kind of U shape here. And the thing that I found very interesting when these results popped up, okay, so each data point for the final L2 error and final H2 error, I mean, these correspond to the same solution. Okay, so I did a simulation with W equal to 10 to the minus 2. At the end of the simulation, I know that measure the L2 and H2 errors. Same for the next data point, and so on and so forth. Now, if my weight in this experiment were 10 to the 2, then I get the best result as far as the L2 error is concerned. If I'm interested in the H2 error, then that's not the case. The weight, the optimal weight in this experiment was 10 to the minus 1. Okay. Now, the thing I've said a couple of times, if I change one thing, then everything might change. Right? If I change the architecture, if I change the amount of iterations that I did, etc., etc. But the qualitative information that we can draw from this is that, okay, the quality of our result is dependent on this W that we choose, and the quality of our result depends on what we choose as our measure of the quality, right? Something which is good for H2 approximation might be bad for L2 approximation. If we're interested in approximating in the thing we're really interested in, for example, or a flux, this would be somehow related to H1 ones. Right? So something that's good in L2 might be horrible in H1, and so on and so forth. Questions or comments up to this point? So I mean, there has been work on how to try and work out what these parameters should be in order to try and get the solution to do what you want. That year is definitely wrong. I think this is 22. It should say here, right? Yeah, 22. So there's two works that I'm citing here. I mean, so this first one, so this is based on the idea of what's called neural tangent kernels. Okay, this is kind of morally the idea is that you have some description of your neural network, and then you can essentially write a kind of evolution equation in an appropriate linearized limit of what SGD scheme is going to do to your solution. And then by doing some horrifically expensive calculation, it can tell you how you should choose the weights in order to get a good solution. Okay, this is very technical, it's very elegant, but this is extremely expensive and not really practical. Okay, so this is a kind of result that's really more informative on the kind of mechanisms that are there behind, but it's not really going to be helpful to actually employ during a training loop, at least in the way that it's presented in the work that they have. Empirically, in all of the cases they considered where they did these calculations that you shouldn't be doing in a practical case, the rule of thumb that they identified is that the order of the term should somehow be inverse to its weight. Okay, so if you have a second order term, okay, we can say this could be order 1. Then a first order term, so something like a Neumann condition, this should be a couple of orders of magnitudes higher. And then Dirichlet conditions, these are now order 0. These should have much bigger weights. Okay, but this is a rule of thumb, which is whenever I'm doing things, I try with this in mind. Sometimes it works, sometimes it doesn't. Okay, because as I say, this all depends on the particular problem that you're considering. And as well, it's not just dependent on the problem, it's dependent on the current state of your system. Right? You have an iterative process. You do some linearization to decide how this thing should change. You get some best solution. Now you change your parameters. Your linearization is different. It tells you should change your parameters in a different way. Right? I mean, things should be evolving in some sense if you want to be optimal, but how to actually access this is very, very complicated. And another work, which again, I mean, this falls under the same category of an incredibly interesting article to read, but not really practical in order to try and put this into your computer. When they try to understand this from the point of view of conditioning on the PDE itself, and somehow they understand the choice of weights that you put in your loss as a kind of preconditioning, and they did some very nice analysis around this. But again, actually extracting the information, what these weights should be, this is really, really expensive and not really practical at the moment. So I made this comment that there's something that we should really be careful of if we're talking about boundary conditions and putting something like the L2 error of a Dirichlet condition into the loss. I mean, mathematically, this is kind of incorrect. Right? If we have some function which is in H2, okay, yes, its boundary value is going to be L2 on the boundary, but in reality, it's going to be much more. Right? I mean, not every single L2 function on the boundary gives rise to something in H2. The same holds if we're only interested in H1, something like weak formulations. I mean, the natural space, if we have H2 functions, would be to have the boundary space is H3/2. Horrible fractional Sobolev spaces involving non-local stuff, horrible double integrals with singular kernels. I mean, these things are really, really hard to access, especially in the context of neural networks. The same thing happens if we have some kind of weak formulation. So we're naturally in H1. Okay, our boundary values are naturally in H1/2, which again, this is still a really complicated space. And using the L2 norm in principle is kind of inconsistent with the mathematical formulation of the problem. So we have essentially two options ahead of us, well, three options. We can just decide we don't care and go for it anyway, which is what plenty of people do, and surprisingly, it works most of the time. We could try to integrate the correct function spaces, but then this is incredibly complicated. Or we can cheat and change our architecture to enforce the boundary conditions that we want. Okay, so if we just think of the really, really simple case of a Dirichlet condition on some smooth boundary, then what we can do is what's called, depending on the author, strong imposition or pinning. So we just find some smooth function defined up to on the closure of our domain of interest. And if we have Dirichlet conditions on the entire boundary, we just say, well, this function has to be 0 on the boundary, positive on the interior. And then we just multiply our neural network. Okay, we think of this U tilde. This is just a classical, fully connected feed-forward neural network. It can do whatever it wants. Now we multiply it by phi. Now on the interior, it can still do more or less whatever it wants. Right? We take this phi to be some nice smooth function. It's positive, so it's not forcing any kind of values. But once we hit the boundary, well, phi is 0, so it doesn't matter what the value here is. All of this disappears. Right? So we have a cutoff function that enforces 0 at the boundary. Now, if we can find some lift, if we have an inhomogeneous Dirichlet condition, then we just find any function which is in our function space and has the correct value on the boundary. Then we add it afterwards, and now we have a function which exists exactly in the function space that we're interested in, right? I mean, like a conforming numerical method would have all of these boundary conditions in the function space itself. We've effectively replicated this with a neural network. Again, if you can find this function and if you can find this function, this is a one-line change of code, essentially, right? I mean, there's nothing particularly complicated about it. So just to be really, really explicit, if we want to consider a problem on 0, 1, we have inhomogeneous Dirichlet conditions at either end, then we can define our neural network to be x times 1 minus x times the output of some fully connected feed-forward neural network with whatever architecture we want. Then afterwards, we just add this linear guy to make sure that it satisfies the correct boundary conditions. Okay. So we go back to this really simple problem that we had on the disk. So again, we're still in 2 dimensions. Because we're on the disk, we can construct a cutoff function really, really simply. And then we can just take phi to be 1 minus x squared minus y squared on the disk. So what I've done in this experiment is I've taken the optimal weight, and this is in the H2 sense, if I should have written it there. But I think this is optimal for the H2 sense And I take the best result when I was using weighting and I compare it to the case where I do this pinning approach. And what we see is that, okay, at the start, things are a little bit different, but it hasn't really started to do anything yet. Then once we actually start optimizing, then we have much better results. Okay, so, and I am a very big fan of these pinning methods, I mean, really for two reasons. One is that as a mathematician, I mean, the functional analysis framework is correct, right? We have a conforming method, so I mean, this somehow makes it much more natural than using unnatural L2 norms. Then as a person with very little patience, it's one less thing to worry about, right? I mean, I don't have to worry about choosing the correct weight. I don't need to worry about integrating correctly, right? So if we're in 2 dimensions, the L2 norm is another integral. This is more quadrature. These are more errors. These are just more spaces to introduce more degrees of freedom that make it harder to get to a good solution. Right? So just by forgetting about one of the parts of my loss, by putting it into the architecture instead, things generally work much better and at the very least are much easier to optimize. When I say optimize, I mean choosing the correct architectures, choosing the correct losses, and so on and so forth. Now, the ability to do pinning is very much dependent on your ability to find a cutoff function that does what you want. Okay, now, this is now where we get into the world of geometry. Now, if we're in 1 dimension, I mean, things are obvious. You can choose a quadratic that's always going to do what you want. I mean, even once we get into 2 dimensions, things get a little bit trickier. In 2 dimensions, if we have a convex polygon, then it's more or less easy to do, right? If you have a convex polygon, then you can identify all of its faces, all of its edges with some hyperplane. All of these hyperplanes are represented by linear equations. So you just multiply all of these linear objects together. And what you get is that, okay, so the one that corresponds to this guy, this could be, for example, negative here, positive here. You do the same with one which cuts through this line. You get something positive here, negative here. You multiply all these guys together. Now you have something which is exactly equal to 0 on the boundary and positive on the interior. This only works if you have a convex polygon. I mean, you think of something like the L shape. If you multiply by a cutoff function that goes through this region, now your neural network is forced to be 0 in the interior, and maybe your solution isn't. Right? It's like this only works if it's convex. But this also comes with a little problem that if we think, okay, let's just do some very, very dirty estimation, what we have is that on this bit of the boundary, our cutoff function is going to be kind of like the distance to the boundary. The same here, but now we multiply the 2 together, we get something like the distance squared. I mean, this kind of forces at the vertices your neural network to be very small. I mean, it kind of can't be more than quadratic, or less than quadratic, I guess I should say, okay? So if you have very, very smooth solutions, this isn't a problem, but if you expect to have something like a little bit more singular in these corners, then you're going to have a problem because you're forcing too much smoothness at the vertex. So one approach, so this was from Barone and his group, put the reference down there. So in this article in general, I would say is very much worth having a read because they don't just propose this, they do a comparison of various methods for imposing boundary conditions when solving PDEs, mostly in the 2-dimensional case. So one of their ideas that they proposed in this article was to think of, okay, if we have some polygon, we can describe its boundary by a bunch of line segments. And the idea is, okay, if we have a line segment, which we think of this white bit here, then we can look at the function, which is the distance to the line, okay? Apart from at these vertices, this is a nice smooth function, essentially. And the idea is that by taking, if we think that each of these phi n's corresponds to this kind of function corresponding to one edge of our polygonal domain, by doing this object, which is kind of like a harmonic squared mean, I guess, now what you get here is precisely the kind of cutoff function that we want. This is going to be equal, I guess, it's indeterminate at the boundary, but at the boundary, it gives you 0. And on the interior, it's always going to give you something positive. And this easily works in the case of non-convex polygons as well, okay, because it's based on line segments rather than infinite lines. As well, even though you might think this is quite dangerous because these functions are going to 0 at the boundary, you do a 1 over, but then you do another 1 over at the end. And as well, the normal derivative of this cutoff function stays bounded. In fact, it tends to 1 when you're near the boundary. So at least to first order, this isn't introducing big problems. Where it does introduce problems is on the vertices. Okay, so what I said before, when you do this idea of just multiplying, go back here, by multiplying by these linear guys, you end up with something kind of too small at this vertex. When you use this, you might end up with something too singular at the vertex. Okay, so balance depending on what you expect from your solutions, I guess. So I mean, something that I really, really want to emphasize, I mean, the way that essential boundary conditions are imposed, I mean, this can be quite a delicate game. And I mean, I think it's really important to keep in mind, I mean, what are the function spaces that you're dealing with when you have your loss function now? In what sense do I want to have a good solution? And is my loss function somehow consistent with the type of approximation that I want? If you go the route of using penalty methods, okay, then you're going to have all kinds of differences in the behavior depending on the weight that you've chosen. Whilst there is some theory there, I mean, it's very difficult to actually apply it to any kind of realistic problem. Pinning is a very, very attractive alternative approach. I am personally a very big fan of it. But it does become very, very tricky once you're in a non-trivial geometry. Okay, this is very easy if you're in squares, disks, whatever. But if you're on the surface of a windmill, okay, then it becomes a very different game. Any questions or comments up to this point? Okay. So one thing that I want to talk about here quickly is just we've only really been thinking of, I mean, essentially classical numerical analysis type problems. I have some PDE, I want to have its solution. Now, one thing that we can do with this kind of framework is something which is a little bit different, but really is just a kind of one-line change of code, but shows the kind of differences in the capabilities of these kinds of models. So what we can think of is, this is a really, really toy model. We know that we have some physical system, and we know that the solution satisfies some constant, Laplacian of u, is equal to a known right-hand side. Okay, this could be saying, okay, we know we have some kind of conductive material or whatever, but we don't know its resistivity, and we know what the forcing is. So we know the physics up to some unknown constant, but we don't know the constant itself. And what we also know are some kind of measurements of the solution, okay? I'm doing this with the measurements themselves. They could be measurements of the derivative. I mean, they could be anything. Now, what we could do is say, okay, I have some noisy data. Maybe I have very, very little data, and I want to find my solution on the rest of the domain. But what's the problem? I don't exactly know the physics because I don't know what this constant is. And I know the PDE it satisfies, but I don't know the material properties that are hiding underneath. So what I could do is say, well, I'm going to consider some kind of interpolation flavored loss, which in isolation, this would be pretty dangerous because maybe I have very little data and it might be very noisy. But then the idea is that if we stick this kind of pins type loss in as well, allowing this to be another trainable variable, this kind of acts like a regularizer. Why? Because Monte Carlo integration is basically free and stops overfitting, right? We can generate infinite data in a certain sense for this part, and then we hope that this stops overfitting. And if we have some kind of near minimizer to this guy, I mean, we know that our solution has to be somehow smooth. But we can also allow during our training process this K to optimize to try and make things minimized, right? So essentially what we're saying is, I have some noisy data, I have an unknown material parameter, I know that I satisfy Poisson's equation with some constant. Can I glue all of this information together to try and get an extrapolation of my data, even though I have a very small amount of data that might be very noisy? Okay? Now, going from known K only with this to unknown K with this term, this is literally like 3 lines of code difference. I mean, we already have a horrifically nonlinear problem here, and a non-convex problem, because the neural network makes the problem horrifically non-convex. I mean, there's almost no difference in terms of computational cost or complexity in considering this problem in comparison to considering just a single forward problem where I want to solve the Laplace equation with a known constant. And again, emphasizing this point, because Monte Carlo gives us infinite data to be able to overfit, which hopefully means that this term doesn't overfit. So in this case, and you can see, I think what this is, 20 data points or something like this. And this was the solution that I obtained. This was my exact solution. And this was the error that we had here, right? So I mean, all of these data points had some noise. In a lot of the examples that I show, okay, I did a few versions of it to try and see how well these things showed up and if they're showing the kind of things I wanted to. This was the very first implementation I did for this problem. I was like, oh, it actually works. So that was quite surprising without having to change the weights or anything like that. So as a part of this process, okay, this constant here, this was another trainable parameter, right? So I'm not only trying to say U satisfies Poisson's equation, I'm saying U satisfies Poisson's equation with an unknown constant, and I'm also adapting the constant in such a way that it fits to the data. And in this particular experiment, I reclaimed the K, which was 1 to within about 5%, something like this. So we can interpret this problem really in one of 2 ways. And the first way is I want to extrapolate noisy data, knowing the physics, but not knowing the physics at the level of the PDE, but not at the level of the material constants. Or we can think of this as a kind of inverse problem, where we have some kind of measurements and we want to identify what the material parameters are. Okay, it really depends on whether our interest is having the solution as good or having this parameter K as good. So obviously you can make inverse problems much more complicated. I mean, this is a really simple toy example, but the key point within all of this is that this just amounted to a really small change in the training process. I mean, you can kind of solve inverse problems in this kind of framework in a 1-step process. And it's the same process as solving the PDE, which still takes forever. It still takes thousands of iterations or whatever. But with a very small change, now you can do a problem, which if you're thinking of something like finite elements, you would have to do a completely whole new problem. Right? I mean, solving Poisson's equation with finite elements versus solving an inverse problem that comes from Poisson's equation using finite elements. There's a huge jump there. But with this, 3 lines of code. So, okay, I think all of this I commented on quite nicely. I mean, please, if there's questions, comments. Okay. So, okay, all the things I've been talking about before, I mean, we've been talking about when we have strong solutions, okay? We're solving some 2nd-order equation and all the derivatives exist in some sense without having to go into weak formulations. But I mean, sometimes we're interested in weak formulations, and then we have to think about what kind of loss functions might be correct to use in these kinds of situations. So if we want to consider Poisson's equation, once again, we're going to be thinking about Dirichlet conditions. Then what we have is our weak form is going to be like this, right? We want to find some U such that for every test function in H10, gradient U dot gradient V plus FV is equal to 0. Okay? Now, again, we have this issue with boundary spaces, and the boundary space, if we're in H1, this is naturally H half, which is a kind of complicated space, certainly more complicated than L2. So we can try to do some kind of penalty method, or we can just make life easier and use pinning and completely forget about what's happening on the boundary. Again, for simplicity, I'm going to be taking a homogeneous Dirichlet condition. So in one method, which, okay, this only really applies to positive, definite, symmetric, elliptic PDEs, is the deep Ritz method. Okay, so this is quite a nice test example for talking about the methods that people use with weak formulations, because it shares a lot of their properties, but it's much simpler. So the idea is that we have an energy written in this form. This depends only on our trial function, our potential solution to the PDE. And we take this energy, half gradient u squared plus fu, and we can classify the critical points of this energy, which have got the solution of the Euler-Lagrange equation. This gives us Poisson's equation. So in particular, this is based on the weak formulation. So the Euler-Lagrange equation is given in weak form, and we have an error estimate of this form. Okay, so if we have our loss function, we take away the minimum value, then our distance to the minimum value is up to some constants and exponents, precisely the error in the H1 node. Okay? So if we're interested in good H1 solutions, then this is a very, very natural choice of loss function to consider, right? Because minimizing the loss is precisely minimizing the error in H1. But obviously we can't do this unless we know what U star is. We can do this knowing only the Laplacian. So integration in the deep Ritz method, this is a horrible, horrible beast. Okay. So when we had physics informed neural networks type losses, strong formulation losses based on L2 norms, basically, we were just summing the residual at certain integration point squared. Okay. Somehow, what this means is that at every integration point, the lowest it can be is 0. And if it's 0 at every single point, if we have a minimizer at each point in our domain, then this is also a global minimizer, right? Minimizing pointwise and minimizing the loss itself are equivalent. Right? If we minimize pointwise everywhere, we minimize everything. The deep Ritz method does not have this property. Okay, if we think of a fixed integration rule, okay, I've said a midpoint rule to be definite, but any fixed integration rule will have this problem. Then we're approximating this loss function by something like 1 over n sum of our integrand at these integration points that we have here. Now, what happens if we do a training using these fixed integration points? So here I have like 10, 15 points or something like that. So, okay, we'll start looking over here. So the exact minimum of my loss function, when I say loss function, I mean in the continuum, is this value here, which is like minus 4.5, right? This characterization as the minimum, which we had wherever it was here, what this means is that if I don't have integration errors, it's impossible for me to evaluate this loss as less than minus 4.5. After about 1,000 iterations, my loss at the discretized sense is like minus 10. What this is saying is I have really, really big integration errors. Right? If my numerical approximation of an integral is less than its theoretical minimum by a factor of 2, something really bad is happening. And by looking at the solution, so here we have the exact solution, which is just some kind of sine 3x kind of guy. And then here we have the approximate solution that we got by doing this optimization scheme. We can kind of see a little bit clearly, or more clearly, what's going on. And maybe, especially people at the back probably can't see this, but if you follow the solution here, right at the integration point, we have a local maximum. What does that mean? The derivative is 0. But also the value is much higher than it should be. And you can kind of work out by looking at this, what's going on. At this integration point, my derivative is 0, right? So this guy is at its minimum, right? And this is something squared. It can't be less than 0, right? But it can be 0. Then its value, right? There's no derivatives here. is large, well, in this case, f is negative from this point. So what this is doing is this is sending this guy to 0 and this guy to minus infinity. And because the derivative and the function itself are kind of independent at independent points, well, you can do this, right? I mean, this giant jump in the derivative that we have here is not seen when we used fixed quadrature. So what I'm really trying to get at here is that when you have some kind of loss function like this, that isn't simply a sum of squares at residuals, you have to be really, really careful when you're doing integration, because the worst case scenario can be really, really bad. Right? I mean, if you're doing a pins type loss, which is just a sum of squares, this kind of catastrophic stuff doesn't tend to happen. But every single time I've tried putting something like this in with deterministic integration, okay, maybe you see this at 1,000 iterations, maybe you see it at 10,000 iterations, but it always blows up really, really quickly. Another thing worth pointing out is that a lot of losses based on weak formulations suffer from properties similar to this, even though they're not exactly the same. I mean, strong formulation type losses are based on sums of squares and don't tend to have as much sensitivity to this kind of issue. But other loss functions based on weak formulations have this kind of structure where you're not just summing squares, you have some kind of integral that can be positive or negative, and integrating poorly can lead things to be unbounded. Okay? So this is something common to other weak formulations as well. Now, when we were talking about pins, we did a comparison of stratified Monte Carlo and regular Monte Carlo. And what we saw was that there was a slight improvement, I mean, that's a very visible improvement, but not huge, when we use stratified Monte Carlo. Now, this is exactly the same problem, again, with Monte Carlo and stratified Monte Carlo, but now I'm using the deep Ritz method rather than pins. Okay, so all of my discussion before was that deep Ritz type losses are incredibly sensitive to integration problems. And here you can see it on a much larger scale. And what we have here is that this purple guy, this is the loss per iteration measured when using standard Monte Carlo. And the blue guy is using a stratified Monte Carlo. Same initialization, same right-hand side. The only difference is that I'm using a different integration scheme with the same number of points in between the two implementations. And you can see, I mean, you can visibly see this is the loss, the amount of fluctuation that we have when we're integrating using the Monte Carlo scheme. I mean, there's basically more noise than there is integral. Whereas the other guy, the stratified Monte Carlo scheme, I mean, nowhere near as noisy. And if we look at the errors versus epochs, I mean, this is starting to get to be a very, very good solution towards the end of training. I mean, this is still quite a short optimization, and I think it's like a few thousand. Okay. But we do see a huge marked improvement here. And again, this comes back to this issue when weak formulation type losses tend to be much more sensitive to integration errors than pins type losses. Another thing that I want to kind of emphasize here, so this property of being a sum of squares, this can also be called the interpolation property. Now, this has a really, really interesting property that if you get very close to a minimizer, or global minimizer of a sum of squares type loss, even if you have integration errors, the integration errors go down the closer you are to the solution, right? Because you're sort of summing something squared. So the derivative is like twice the error. If the error is 0, this is 0, right? So the closer you get to the minimum when doing a pins type problem, the less integration error you typically have. I mean, it's sort of self-improving as you converge. And this is not the case when you have a deep Ritz type problem. I mean, you kind of reach a steady state and your integration errors are sort of fixed, shall we say, an order 1. So this makes things much harder to at the level of whether you're converging to a solution. And it also makes the solution itself much less stable, right? You can be at the exact solution in the deep Ritz method. You do one iteration, and because of integration errors, you're now in a really bad solution. This doesn't happen if you have a sum of squares. you have a sum of squares type loss, if you're at the exact solution, even if you have integration errors, then your derivative is going to be 0 and you don't change your weights. Okay, so they're much more stable in an optimization loop. And a lot of these properties, I mean, that are quite common when we're talking about other losses involving weak formulations. So one thing that I want to add, okay, so if we have the Diepritz method, I mean, these tend to be, I've only been talking about smooth solutions, but if we have irregular solutions, then the Diepritz admits a very, very similar type of relationships. Okay. In this case, if we have this sigma to be discontinuous, we cannot accept H2 solutions, right? We have jumps over interfaces. The second derivative doesn't exist as such. So we have to use some kind of method for weak solutions. So, I mean, it's not just, we can't just say, well, okay, let's just use sum of squares pins losses for everything. I mean, there are some problems that need you to use methods based on weak formulations, and then you're going to start entering into these kinds of problems. So I think it's this session, there's probably a good spot to break now, right? Because it was until 1:30. That's it. No, some of this stuff I can jump onto tomorrow. I think it's probably a good place to stop the day. Okay. 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 Yep.
So what do you mean by weight metrics and like
Okay, so when I'm talking about satisfying a weak formulation, what I mean is that we have some U, which, okay, in the simplest case, if we have Dirichlet conditions, okay, all I'm requiring is that my U almost have a gradient, which is well defined, right? And what I want is that if I have some test function, okay, then okay, if I do this kind of integral, then I get 0, right? So the strong formulation would be the pointwise guy saying something like this, right? Now, if I have a solution of this, and I multiply by a test function, integrate by parts, then I get this. Okay, so this implies this, but going backwards is not the case, right? If I have some kind of a regular solution with interfaces or whatever, it may be that it still satisfies this, which in many applications, this is somehow the real equation. But because the solution isn't regular enough, I can't do integration by parts to get to this guy. Okay, so this is why it's strong, because if it satisfies this, then it satisfies this. Yeah.
Yeah, one question. When you train also the parameter equation,
Mhm.
that depends on the number of physical solution number of points. So I guess also the number of points they get you to optimality or
So you're talking about in this problem,
yeah,
right? But do you mean the points in this data set?
yes.
Oh, okay, so in this really toy example, I'm thinking of these points as being fixed because they come from physical real data, which is expensive. Yeah. Okay, so here I think of synthetic data that I make from Monte Carlo. And then here I think, okay, I just have this small sample and I can't do anything more than that. Okay, so they're given at the start and they're fixed and I can't do anything else with them afterwards. But okay, I mean, you could do 100 different variations on this problem. I mean, whether they make sense in the real world is a different story, right? I mean,
Question. What question? Thank again, Jim. In the version tomorrow at 10:30.